Okay, good evening all. I think we can start the class. So actually today basically we'll discuss whatever we have learned here. So that we'll summarize. So before that, what we'll do, uh, we can see as I have mentioned that I'll show how to do the cyclic voltammetry and potentiostat. So that things I will show today and some video we have done, so that experiment I will show, and after that we'll summarize whatever we have learned earlier class. Okay, so I think yeah, I think I can share from here maybe. Okay. Yeah, see. Yeah, I hope everyone is able to see. Okay, how to do the full screen. Hmm. Okay, so I think all people can see the screen. So basically, this is what we are doing. We want to know the diffusion coefficient as I think Randle-Sevig equation. We have there is one equation I think during the cyclic voltammetry discussion I have mentioned that part. So basically, we want to know the diffusion coefficient of iron hexaferricyanate. So from cyclic voltammetry, you can what information you can get different redox potential where it is reducing and where it is oxidizing. That potential you can get, and what are the number of electrons if this is 2 electron process or 1 electron process, that information you can get. Other thing, the diffusion coefficient, as I have mentioned that the current value in voltammogram, that depends on three type of current value is there. One is diffusion current, other one is migration current, other one is convection current. So the cyclic voltammetry, that is basically we are measuring the diffusion current because we are using the supporting electrolyte which can minimize other migration current. So and convection current, we are keeping the cell in static condition. So in that case we are basically minimizing the convection current. Okay, so in this video I will show how to prepare the solution step by step, all the things I will show. So we can play the video. So I hope people can see the things. So basically first things is preparation of 0.2 molar KNO3, which is acting as a supporting electrolyte. So in aqueous solution, basically to do the experiment, we need supporting electrolyte, which can minimize the migration current. So here 0.2 molar KNO3 solution in I think 250 ml volumetric flux or 250 ml distilled water. So for that we need 5.05 gram of it is called potassium nitrate. So for this, and we are just measuring that one. So then, that one, I think, yeah, it is 5.055 grams. So then we can put this one to 50 ml volumetric flask. So I think the solution measurement, we already discussed how to make the solution property. I think second class we have discussed the solution properties. One is we measure what is called different type of concentration terms like molarity, parts per million, all these things. So here you can see we are making 0.2 molar of KNO3 solution. So that is also, this is one of the practical thing that how we can measure suppose 0.2 molar of solution in 250 ml of solution you want to make. Then you can take a volumetric flask which is 250 ml of volumetric flask. There is a mark, so from here you can make the exact concentration of solution. So this is the thing. Then you can dissolve the electrolyte and you can make the solution at 250 ml of solution. Okay, so and from here we will do the, you can see now there is a mark, so it is called volume makeup. So you can up to whatever mark is there, that is for 250 ml. So up to that you can make the solution. I think all people can know this thing in BSc level or MSc level. You did the practical, so that time you used to make this kind of thing. So after that we will make, I think preparation of 20 millimolar of potassium ferricyanate solution where iron is plus 3 oxidation state. So this is ferric ferrous solution. So you will get the redox couple of iron plus 2 plus 3 redox couple you will get. So and this thing is that for that you need 0.658 gram of ferric cyanide solution. So which is I think like a brown color solution, so compound. So and from here we will make different concentration of ferricyanide, and from there we will measure the cyclic voltammogram for different concentration of the compound. Okay. And step by step I will show that how what is the electrochemical cell, and how looks like the working electrode, reference electrode, and counter electrode. All these things we will see in this video. And these things I think how to looks like the potentiostat, and how to do in potentiostat, how to measure the open circuit potential. All these things we'll see in this video. Okay, so I can little bit I can fast it. So after the whatever we are making in 100 kml volumetric flask to transfer, how to make the solution in volumetric flask. So that I think all people know these things. And when we will do the makeup or fill the solution, we will make the solution with the supporting electrolyte whatever we make earlier, 250 ml of the solution. Okay, so basically from the earlier volumetric flask, we put the solution here, and we'll in the similar way whatever earlier way we make the volume makeup. So same way we have done for that. Okay. So now from here we want to make 5 different concentration of solution. So I think 60 millimolar, 12 millimolar, 8 millimolar, 4 millimolar. So different concentration of solution you want to make. So here it is mentioned the 16, 12, 8, 4 millimolar solution you want to make. So as we know that V1S1 is equal to V2S2, that formula. So you can calculate that initially it is I think 200 millimolar or something. So from there how you can dilute the solution, and you can make the different concentration of solution. So this is basically that part. I think all people know this part. So whatever we are taking, that is the burette we used to call. So in burette you used to get the exact amount. So from here you can get that this value we are taking how much the concentration is required for 10 ml of solution. So from 20 millimolar solution, how to make the 8 ml we have to do it, as I think it is shown in the video. So 8 ml solution, and remaining thing 16 millimolar of this solution we want to make, and from there whatever 8 ml we have taken, so remaining 2 ml of supporting electrolyte you can add. So in general, during the cyclic voltammetry, what you used to do, that whatever your analyte, whatever concentration, supporting electrolyte should be 100 times or 200 times higher compared to the whatever solution, whatever analyte concentration. So here, whatever KNO3, we have made that 0.2 molar of concentration of KNO3, but all the analyte, that is K3 FeCN whole 6. So that things we have taken here is 20 millimolar maximum, and other all are 16 millimolar and 8 millimolar, 12 millimolar. So all are in the millimolar, and the supporting electrolyte, that is in 0.2 molar. So around 100 times higher concentration. So in general, we used to take higher concentration of supporting electrolyte because we want to minimize the migration current. Okay, so that is the thing. So I think this part we can skip a little bit. So basically, this is different concentration of electrolyte we are making, so that we can take the concentration dependent cyclic voltammogram. From there we can get different type of information, like what is called rate constant for the redox process, then diffusion coefficient, all these things information you can get. Okay, so you just make like this, so that it will make the homogeneous solution. Okay, so this is basically, now I will show what are the electrolytes. So this black one that is you are seeing, so this is the working electrode. In general, the working electrode surface area should be lower than the counter electrode. So as I have mentioned, that counter electrode, what is the function of counter electrode, or three electrode setup, what are the function? In counter working electrode, you used to see what are the redox process is happening. So in that case, and counter electrode, it is there due to the measurement of current, and reference electrode to measure the potential in between the working electrode and reference electrode. Okay, so these things we have discussed. So as we are measuring the current in between the working electrode and counter electrode, so that means the counter electrode surface area should be higher, so that electron transfer can happen easily. As we know that as the surface area is, or area of the electrode will high, then the current value will be high, right? So that because as we know Ohm's law, rho is equal to L by A. So as A is increased, then R will be decreased. R will means resistance will decrease. So resistance decrease means your current value will be high, right? So that's why. But the working electrode surface area should be lower than the counter electrode. So this is the platinum disc working electrode. Here you can see that it is kind of this kind of shining part is there. So this is only the conducting part, and other black part, that is the insulating part. So that whatever reaction will happen in this part only. So you can get the current value, and we can get the current density. We know that how much area of this shining part. I think it is the dia is 2 mm. So from there you can get how much potential, how much area of that electrode, and you can whatever current value you will get, you can divide that part. Okay, so you can see that this is the working part. Now whatever we are using this working electrode, suppose someone used in earlier, then whatever different compound suppose someone used, so that compound can deposit it on your working electrode. So for that, what people used to do, you have to clean the working electrode. So for cleaning the working electrode, we use alumina powder. So different type of different grade of aluminum powder is there. Basically this grade means different size particle size alumina powder is there, like 0.05 micrometer or point 0.3 micrometer, 1 micrometer. So different grading alumina powder is there. So in this, here there is uh, white powder it is showing, so that is the alumina powder. So we have to add the little bit of water, and then we have to clean the working electrode. And when you have to clean the working electrode, we have to draw basically 8 English 8. So polishing the working electrode, and after polish the working electrode, you have to wash properly the working electrode, because if the alumina powder is there on the working electrode surface, that can affect your redox couple or in the working surface, means whatever working surface is there. So then you have to clean the working electrode. Okay, and this is the reference electrode. So this is AgAgCl reference electrode, where you can see in this glass inside some what is called wire you can see. So that is the silver wire, and in it is what is called, there is a glass wire is what is called glass tube is there, and in this glass tube silver wire is there, and that is filled with 1 molar KCl solution or 0.3 molar 3 molar KCl solution. Because it is called this silver chloride reference electrode potential, that is depend on the concentration of Cl minus or activity of Cl minus. So for AgAgCl, the reference potential is 0.197 volt with respect to standard hydrogen electrode. So that things we already discussed, that how the reference electrode looks like. So glassy carbon also it is to there. Okay, so this is this blue one, that is basically cap. You can remove the things. After that, I will show. Uh, yeah, so this you can see this white part. So this white part basically the you call frit. So this frit basically it is ionically conducting. So earlier, whatever you see that you have two container, and in these two container which is separated by the salt bridge. So what is the function of salt bridge? That we movement the potassium ion or NO3 minus ion, so that there will be a ion connection between two beaker. So in this case, your what is called reference electrode or electrolyte, it will be there in one electrochemical cell. So in this electrochemical cell, your reference electrode is separated by a ion transporting fluid. So basically, it will transport the ion. It will not mix with the electrolyte. Okay. So that you can see this fluid kind of thing, and this is the working electrode. So you have to rinse. So, and this silver chloride, it is to store in 1 molar KCl solution or saturated KCl solution, so that your fluid whatever things is there, that can be that cannot be dry. If it is dry, then whatever silver salt is there, silver chloride, that will deposit in the fluid, so that will seal the porosity of the fluid, so that you will not able to measure whatever or whatever potential, that will not give the appropriate potential. Suppose iron redox couple, that is to give the potential at 0.7 volt, but if your reference electrode potential is not exact reference potential, like in the case of silver chloride AgAgCl reference electrode, that is 0.197, but somehow suppose your potential is changed to 0.197 volt to suppose zero point 0.3 volt, then whatever potential difference 0.1 volt, that will also show in your redox couple potential position. Okay, so here you can see, so this HEAGCl, this is the reference electrode, and this is your working electrode, and this is your counter electrode, platinum wire. So you can see this platinum wire, whole things will dip in the whole things, no, maximum 40 to 50% of the wire, this wire will dip in the solution. So the working potential, this working what is called area of this counter electrode will be high compared to your working electrode area. Okay, now this is the things. Now I think, yeah. So, and this is the what is called electrochemical cell. So this is the electrochemical cell, whatever we have shown, we have discussed in the class. So this is the electrochemical cell. You can put your sample or electrolyte here, and this is your cap. There you can see three big hole is there, which is you can put one is for reference electrode, one for counter electrode, and one for working electrode, and all these three are separated in equal distance, and there is also small hole is there, this one. So that is for the what is called gas purging. Suppose you want to do in some inert condition or in your sample, suppose oxygen is dissolved in your sample, then what will happen that you can that oxygen can affect your redox couple. So for this, what people is to do that they purge the solution with different inert gas like nitrogen or argon gas, which is inert in working condition, so that you can get whatever redox couple from the compound, it will not affect in the redox couple due to the oxygen. So for that, these two holes is there, for one is for in and other one is for out. Okay, so and this is the potentiostat. So this black color, I think okay, oh yeah, so this black color box you can see. Okay, this is, you can see, so this is the basically the potentiostat we used to tell, because you can apply the potential and you can measure the current. So the instrument company name is CH instrument, so electrochemical analytical, basically this is the company name, so which manufacture this potentiostat. So here you can measure the you can apply the potential, and along with that you can measure the current value. So that you will see. So this this is the power button. So you switched on the what is called potential, and it is connected with the PC. Okay, monitor. So you can uh, connect the data. So and we are pouring the first supporting electrolyte, because what we have discussed earlier also, that whatever your supporting electrolytes, that should not show any redox couple in between that potential, where your analyte will show the redox couple. So here our analyte is what is called different concentration of iron hexaferricyanate. So before doing the experiment for ferricyanate, we have to do the experiment for what is called supporting electrolyte solution, so that we can see if there is any activities there of that supporting electrolyte. Okay, and as also we have to know that your solvent, here it is water, so that solvent is stable in that whatever potential window we will measure. So all this information we have to do first. So for this, when we will do the experiment, first we have to do that. First we will take the supporting electrolyte or only the solvent, and you do the CB cyclic voltammetry. Then you will see there is any redox activity of the compound of the solvent or supporting electrolyte is there or not. Okay. After that, we will measure for your analyte. So For that, we are first doing for supporting electrolyte. So we pour the supporting electrolyte and then we tight the cap, and we are tightening the screw so that it cannot be basically go here there. So there should not be any disturbance, because as I have mentioned that to minimize the convection current, we should put the solution in static condition. So for this we tightened the cell and we put three electrodes. So one is working electrode, one is counter electrode and reference electrode. So here you can see this is the electrochemical setup. Okay, so and this black one, that is the working electrode, platinum disc electrode, and this AgAg cell, that is the reference electrode, and platinum is the counter, platinum wire is the counter electrode. So in the instrument also there should be three lead which can connect with the electrochemical cell. So here you can see this blue one. So that is the it is called working electrode lead. So this green one, that is the working electrode lead, and this red one, that is the counter electrode lead. So that counter electrode is connected with the platinum wire counter electrode, and this white one, that is the it is called reference electrode lead. So that is connected with the reference electrode, and there is another lead also there, that is black one. So here you can see it is top of the potentiostat. Okay, so that things is there. So this potential, this black one is basically the grounding. Okay, so this so to run this experiment, there is some software which can connect with the PC and the potentiostat. So the software name is CH instrument. So this CH instrument we have click. So when we will start the CH instrument software, so this kind of interface it will come. So this kind of interface when it will come, so we have to go to the setup value uh, and technique. So there is different in potentiostat, there is different kind of technique is there, like linear shift voltammetry, cyclic voltammetry, then chronoamperometry, chronopotentiometry. This is all are the electrochemical technique or electroanalytical technique. You can do all these experiment, you can go to know different type of information. Okay, like from cyclic voltammetry or linear shift voltammetry, you will get the information of where the redox couple is coming, all these things. And chronoamperometry means basically you can measure the current value as a function of time, and when you will apply the constant potential. And chronopotentiometry means you can measure the voltage as a function of time when you will applying the constant current. So this kind of different kind of electrochemical techniques you can is there, and you can measure. So as you can go to the T, that is for technique, and as you want to do the CV, that is cyclic voltammetry, so you can click the cyclic voltammetry and you can select that. Okay, and before that whatever we have mentioned, that OCV value, open circuit potential. So how you can measure the open circuit potential? So now whatever you connect all three lead with the three different electrode of the of your electrochemical cell. Now we are not applying any potential, right? So that means at without any application of potential, whatever potential we are getting from the cell, that is called open circuit potential. So that things you can measure here. So you can go. So here you can see, although it is not so clear, but it is showing the open circuit potential 0.1968. So that means without any difference of without any application of potential, the potential difference between working electrode and your reference electrode, that is 0.196 volt. Okay, and whenever you will start the experiment, and this open circuit potential, that is the equilibrium potential. Okay, now whenever you will start the experiment, that time what you have to do, that you have to start the experiment from the OCV value, or open circuit potential, because that is the equilibrium state. Now if you start from some other potential, suppose now the potential is 0.196 volt or zero point 0.2 volt, and you start the experiment from suppose 1 volt or something, means there is the difference of 0.8 volt. Okay, so that means you are forcing the system suddenly from to go from 0.2 volt to the 1 volt. Okay, so there means there is a destabilization of the system, so there will be some discrepancy of the result. Okay, for this always it's better to start from the OCV value. Okay, now we get to know that what is the OCV value. Now whatever we have to go to the set parameter the dialog box, where you can give the all the parameter. Okay, because which potential window you want to do the reaction, means which potential window you want to sweep the potential and measure the current. So there is different type of parameter is there. Here you can see INI means initial potential. That means from where you want to start the experiment. And then high E, that is the highest potential. So you will get the voltage window. So there high voltage window, high terminal voltage, and this low E means low terminal voltage. Okay, and this final E, so this finally that is representing that where you want to stop the potential, or where you want to stop the reaction. Okay, and there is the initial scan polarity. So now there is a negative and positive, it is there. So basically which potential direction you want to scan the process. If you want to go fast reduction, then you have to give the polarity as a negative, and if you want to do fast oxidation, then you have to give as a positive polarity. Okay, then other things is there, that is scan rate. So basically their scan rate is that will give the information that with how fast you want to apply the potential. So this scan rate is millivolt per second. Suppose 10 millivolt per second, that means you are applying the potential 10 millivolt in 1 second with respect to your reference electrode. Okay, so here you can see that initial potential I am giving that 0.196. So that is the OCV value we already know. And as I mentioned that we have to start from the OCV value, it's better to start. At some some case we will not able to start in the OCV value, but it's better or standard process to start the reaction from the OCV value. Now higher potential we have given at 0.7 volt, and lower potential minus 0.5 volt. So in this potential window we want to do the what is called cyclic voltammetry, and finally where you want to stop 0.7 volt we want to stop. Okay, and this is the scan rate. So scan rate, it is written volt per second. So I have given 0.1 volt, that is means 100 millivolt per second. And this segment, basically the segment representing that one cyclic voltammogram, one redox couple, so that is the segment. So I will show once again in the when I will summarize the talk. So that time I will show that what is the what is called segment means which one. So there is 4 segment means 2 cycles. So for one cycle there is 2 segment. Okay, so and this is the sensitivity. So basically up to how much current you want to measure. So I have given 1 into e to the minus 4 ampere. That means if your current value of the system is milliampere or microampere level, that can be also instrument can measure. Okay, so now what is called, you can start the experiment. So here you can see that current versus potential curve it is showing, and as it is a what is called only for counter supporting electrolyte, that means there is no redox active species is not there. So for this it is showing a straight line. Okay, and here the time value it is showing, so how much time it will remain to complete the reaction. So here you can see there is no uh, what is called redox active species is not there. That means it should be straight line. As I have mentioned that your supporting electrolyte in this working electrode region should not show any what is called redox activity. Okay. Now this data you can save in your computer. So here I am writing the supporting electrolyte. So that when you will plot the data, there is some software is there like kaleidogram or origin. This is all are the plotting software, so you can measure that thing. So again, this is the working electrochemical cell. Now you can remove the all the lead, and then you can change the electrolyte. Okay, so that before doing the experiment, I can clean the all the electrode also, as we did for supporting electrolyte. So that's why it is not showing what it's called. We are not cleaning because we are doing all the experiment for same compound. So 4 millimolar, first we are doing 4 millimolar K3 FeCN whole 6. Now we are doing for analyte. So K3 FeCN whole 6, that is the analyte. Okay. Now we will see how the K redox couple will show. I hope you people are getting the point how to do the experiment in cyclic voltammetry or in electrochemical cell. So when you are getting some pollutant or something, so this all are the potential. We need the potential stat and this kind of small electrochemical cell we need, and whatever pollutant you get, so that you can put use as electrolyte and all other things you can get. So for plating, electroplating also you can do in these electrochemical cells. So basically you have to take two plate, and you can apply the potential. Okay, so this is for electrolyte. So whatever way that earlier we have done that electrochemical potential, so similar way now we can measure the open circuit potential. So here now you can see that earlier it was 0.197 volt for only for supporting electrolyte. Now you can see it is 0.307 volt. Okay, so that means as your system is changed, your open circuit potential, that means between difference the potential between the working electrode and reference electrode, that is also changed. Okay, and we should measure the open circuit potential every time before start the experiment, so that you can get what is the equilibrium potential or your system it is. Okay, so you can start the experiment from that potential value only. So now we are giving 0.73 volt, and all the uh, potential window we have kept same 0.7 volt to minus 0.8 volt, because we don't know where the redox couple will come. Okay, so for this what people used to do, that initially we have to do in long range of potential window, so that you can get information that where the redox couple is coming. So after that you can sort it out, or you can cut down the potential to window. Okay, now let's see how it is coming. So this here you can see now that nice redox peak is coming. So this dark kind of shape as I have shown earlier also cyclic voltammogram discussion. So this is representing some Faraday reaction. You can see some reversible redox couple it is observing. So this is basically this lower part, this is the reduction. So this reduction basically ferric we have taken. So iron +3 oxidation state it is there. So it is going +3 to +2, and this one is reverse process, that is +2 to +3 redox couple it is showing. So here you can see that a nice redox couple it is showing, and the potential you can see where the potential it is. It is coming around. Here you can see the EP is equal to minus 0.165 volt, that is the peak potential. So and how much peak current value IPE that is giving, so 1.36346 e to the power minus 5 ampere. So all the information you can get, okay, and you can save this data. So means where the redox peak is coming and how much current it is representing coming of the peak current. So all these things you can give. So now again you can measure the potential OCV value, that is around 0.9 and 0.299, earlier 0.307 it is there. So and with different scan rate you can measure, because whatever things is there. So now I think we are, because as this redox couple it is here only, so no need to do at high potential. So for this whatever we are doing, that we are cut down the potential window smaller, so that the graph looks little bit nice. So for this it is given 0. minus 0.1 to 0.64. Okay, now we can run the experiment. And scan rate we have given 0.05 volt, that means 50 millivolt per second. Okay, now we can run the experiment. So you can see nice redox couple is coming. So you can see this redox couple it is showing. So basically from here whatever I have told, that different type of information you can get, redox position, all these things. So you can see nice redox capability is there. Now to calculate the diffusion coefficient, you have to run the experiment in different basically different scan rate, because we have seen the Rayleigh-Sevig equation. So that is IP peak current, that is proportional to the square root of scan rate. So if you plot IP peak current versus square root of scan rate, and from there you will get the information number of electron and diffusion coefficient of iron 3, iron 2 plus and iron 3 plus, and what is called current value also you are getting. So all this information you can get. Okay, so I think different concentration, different scan rate we have done, I think. So I am just cut out all this thing, because it is same only. Okay, so different so we have to clean all this part. Okay, so similar way you can do for different other concentration also. Means other way also, that different other concentration you can do, and along with that we can measure the diffusion coefficient value. So here I want to ask that if you people have any question regarding this experiment, then you can ask now, where you are not getting that how it is happening, all these things, so that I can explain. Whatever I have shown, you people get the point. Okay, so basically this is in what is called research lab, and all these things we used to get this kind of means we used to do this kind of thing. So and I don't know which background you people are. So so many lots of people used to do the project in electrochemistry. So as you people are doing the electrochemical technique in pollution control, so you people can do the master project, or after BSc also you people can do some short project on electrochemistry. So I used to work with Professor Alinda J. Bhattacharya in solid state and structural chemistry unit. So if people are interested, then you can write the mail to the professor. So if he allow to do the project in our lab, then you people can do the it is called project, so that you can get in hand experience how to do the it is called electrochemistry, and how people are doing the battery, all these things. So energy storage application, so that things you can get, so that you people can mail to professor, and you can do the things. So now I think we can summarize another one video, experimental video is there. So I'll show that one in the end, that is the potentiometric titration. So I think earlier, whatever one day I did not able to show that video, so today I can show that video at the end of my class. Okay, so before that I can summarize whatever we have learn in last what is called 8-week course. So that things I think we can do that thing. Okay, so I think let me share the screen. Where is the okay, I think it is here, might be. I think this one, yeah. Okay, so I think whatever we have discussed, as I think all people will know, this is the last class. So I think all the things we have discussed. Just I will not go to details, whatever we have discussed. So just I will summarize whatever we learn. So that we can get that. Okay, these are the things we have discussed. Okay. So the first class we have discussed the introduction. So in the introduction, whatever we have discussed, that why we need to electrochemical technique, how we can control this pollution. So what are the what is called pollution? So technical environmental pollution is thought to originate from dust, chemicals, and their interaction with the microbiological species such as bacteria, virus, algae, fungi, etc. So that kind of things means from where the this pollution is coming. So this is one of the diagram we have shown, that this is the annual report by the Pollution Control Board of Karnataka. As I am staying in Bangalore, so I just took the information. So this is the pollution level of different water, different river water. So basically here Kaveri, Godavari, all this water is there. So how the water is polluting, so this is with time scale. So I think so this is the time scale 2016 to 2021. So here basically representing that this blue one, that different kind of specialization or classified of the pollutant. So A, B, C, D, E, like that. So basically A is drinking water source without conventional treatment, but after disinfection, because there might be some bacteria, all this thing is there. So in the river water, so we need to disinfect that water. And B is the outdoor water or organized water, and C is the drinking water source with conventional treatment followed by disinfection, and D is the propagation of wildlife or fishery, and E is the irrigation or industrial cooling and control waste disposal. So here you can see that earlier this red E, so this is E blue one. So here you can see that most of the thing is increasing, and D number of it is called pollutant number is increasing. So class C, you can see that it is 77%. So that means with time the pollution level is increasing. So for that we need some easy or user friendly technique which can give the information, what are the pollutant is there, how much pollutant is there, all kind of information. Okay, so there is another report we have taken, we have shown in 29 January, that is the some place in Delhi. So this is the report from Central Pollution Control Board. So here you can see that as the number of this pollutant level rate one, that is very hazardous, and you can see here. So this is respiratory illness on prolonged exposure. So as we also know that in Delhi, which is a highly pollutant city, one of the highly pollutant city. So this during the winter season as well as during the summer season, it is very hot and it is highly polluted. So it can affect the health. So you can see the micro particle of this in the air that is increasing, which can affect on the health of human. So that is one of the report that how much pollutant is there in the air. Okay, so these things we have discussed. So for that, now question what we have to do. So if there is a pollution in water or in air, then what we have to do. So there is three things. One is the identification and determination the pollutant and the extent of pollution. And second is the technical intervention. So basically, you have to develop the technique where you can basically we can detect the pollutant and you can minimize the pollution, and then post intervention intervention evaluation. Okay, so these three things we have to do. So polytentally, it is possible employ atomic and molecular spectroscopy. So not only the electrochemical technique is required, spectroscopy also can help to quantify the pollution pollutant concentration. So why now question that why electrochemical technique? Because we have different type of technique also there, like microscopic technique, spectroscopic technique, but why electrochemical technique? Because as I mentioned that it is quite user friendly and easy, and it is what is called non-expensive technique. So electrochemical sensor include ion selective electro, employ a detection of pollutant level in all public space, and it is a highly sensitive in ppm levels or less than that also. If you have the pollutant in ppm level, then that can also give the information of that. Okay, so all these things you have discussed. So fuel cell battery technology for energy source or renewable energy source, I think we already discussed more details about the battery, all these things. Okay, so these are the things we have discussed. Then interpretation of two major branches of chemistry has resulted in researches electrochemical technology due to the enhance of selectivity and sensitivity and heterocyclic to react with the target species. And consequently, majority of this research has transferred in the last 2 decades of this environmental analytical chemistry. Okay, so on the importance of this electrochemical technique. So our course is basically these are the things we have discussed: potentiometry, conductometry, voltammetry, electrochemical sensor, battery, all these things we have, and also process of waste handling, how to control the waste. So all these things we have discussed. Okay, so first class we have discussed some part of basics of atomic structure, some Dalton models we have discussed. Then there is a Bohr model. So Dalton model, what it is to tell that Rutherford model we have discussed. Then Bohr model. So in the Bohr model we have discussed that it is the nucleus. In the nucleus we have neutron, neutral particle, and the positive charge, and around different segregated state, or which is called orbital. In the orbital different number of electron is there. Okay, so that is the more modern atomic level. So from I think okay, why it is not changing. Okay, how come? Okay, it is not changing. There is some issue. Okay. No. Just a minute. This oh my god. Why it is not changing the things? I am also not able to go outside the. Oh, now it is changing. Okay, so basically what you can see that then after that we have discussed the modern atomic orbital. Then I am not going to detail. Then different origin of hydrogen spectroscopy, like Lyman series, Gamma series, Paschen, bracket, Fund series. So basically when your transition is happening from higher energy state to a higher energy atomic orbital to N1 orbital, then that is called Lyman series. And if it is 2 n is equal to 2, then that is called the Barma series. So there is also there is a different small spectrum is there, like alpha, beta, gamma. So if there is coming from 2 to 1, that is alpha. If 3 to 1, that is called beta. Okay, so and also which energy region it will come, that also we have discussed. So this is IR UV region, UVs, and this is visible region, this is UV, and all are the IR region. We have discussed all these things. So and along with that how much the energy of this each state. So that is to represent this equation: minus 2 pi square z square e to the power 4 mu by h square by n 1 by n square. This n is the principal quantum number, like n is equal to 1, 2, like that. And this z is the atomic number, h is the Planck's constant, and mu is the reduced mass of the atom. Okay, so these things we have discussed. Then after that we have discussed the Sommerfeld theory. So Okay, then we have discussed a little bit about the principal quantum number. So how to calculate the principal quantum number? Okay, there is different type of principal quantum number. Then after that, okay, we have discussed angular quantum number, that is represented as L. So if n is equal to a 1, L value okay, will be 0. If n is equal to 2, then L value is 0 and 1. So basically L value represent n minus 1. Okay, so that is the value. So because and if n is equal to 3, then L value will be 0, 1, 2. So like that. And depend on L, we have to the what is called spectrum, like L1, then S orbital, L is equal to 2, P orbital, L is equal to 3, then D orbital, like that. Okay. Then we have discussed about magnetic quantum number. It is represent M value, and spin quantum number, that is S. So all these things we have discussed. Now how to what is called put the electron or fill the electron, that's depend on this rule. So here always each orbital is to have only 2 electrons. So p orbital has 3 states, so 6 electron can happen. So how to enter the electron, that's depend on this. So 1s, then 2s, 2p, 2s, then 3s, like this. So 2s, then 2p, 3s, 3p, like that. Okay, so that way we can fill the electron. So that things we have discussed. Then week 2 we have discussed different solution properties, basically the quantitative manner, whatever I have shown in the video, how to make the solution. So that things basically week 2 we have discussed. So and different type of terms like molar percentage, mass percentage, volume percentage, all these things we have discussed. Okay, so and mass by volume percentage, so parts per million, ppm, ppb, ppt, all these things. Then mole fraction, the number of mole of component divided by total number of mole of all component, that is to represent like xa is equal to na by na plus nb, that is a plus b component. So in that case we used to what is called measure this way, we used to present this way. So this A is the molarity of the mole of the A component, and B is the component mole component of the B. And molarity also we have discussed, and in this video I have shown that how to make the mole solution 0.2 molar of K3 FeCN whole 6. So that things we have discussed. Then molality also we have discussed. Then along with that, last Sutherland principle also we have discussed. What is last Sutherland principle? Basically, suppose you have some system which is in the equilibrium state. Now we put the external force from the outside. So system will respond in that way that the system can minimize that external force. Okay, so suppose you have a water, and we are applying the temperature from the outside. So the water will respond in that way that it can decrease the temperature. So for that, what is to do, that suppose you are continuously applying the 100 degrees Celsius, then what will happen, that water will evaporate, so that it can consume the temperature or heat, and it can minimize the external heat or external temperature. Okay, so like that. After with that, we discuss about the Henry's law. So that partial pressure that's depend on the mole fraction of the solute, and K is the Henry constant. Okay, and Raoult's law also we have discussed. So Raoult's law tell that in a solution or volatile liquid, the partial vapor pressure of each component, each of the solution is directly proportional to the mole fraction of the solute. Okay, so that things we have discussed. So then what we have discussed, that Dalton's law. So basically, total pressure of the any solution is summation of the partial pressure of the each component. So if you have two component P1 and P2, then total pressure will be P1 plus P2. So here in this graph we have discussed that x1 is equal to 0, so this is the partial pressure P1, that is the pure pressure, and x1 0, x2 is 1, that is the pure pressure, partial pressure of x2. And in this, if you mix in different component, then it will give a straight line. So this is the partial pressure or total pressure of the solution. Okay. So, and relative lowering of the vapor pressure, what it is representing, basically it will tell us that if you have a pure solvent and if you put some analyte, then the vapor pressure top of the solution will be decreased. So why it is decreased, that things we have discussed, because whatever in the solution surface, your number of pure solvent material, solvent atom is lower when you are mixing any analyte or any solute in the solution. So in the surface we have solvent molecule also as well as solute molecule also. So it is then less number of solvent molecule is going to the vapor phase. So for this it will lowering the vapor pressure. Okay, so that things we have discussed. Now elevating of the boiling point also. So let me drink little bit water. Elevating of boiling point. So basically it will what is called, this is the solution and this is the solvent. So here you can see it is higher temperature, it is going to the vapor pressure. So from here this del Ta, that is proportional to molarity of the solution. So that things we discuss, and del Ta and del Tb also, del Tb boiling point differentiation of boiling point, that is also proportional to molarity. So from there you can get the constant of freezing point constant, and elevation of the boiling point and freezing point. So that rate constant you can get or calculate. So all these things we have discussed. So many numerical problem also we have discussed. So after that we have discussed the osmotic and osmotic pressure, osmosis and osmotic pressure. So Van of law, basically pi is equal to nRT, so or CRT. So that from here also we have discussed lots of numerical problem. And after that electrolyte dissociation. So basically here we have discussed different type of electrolyte, acid, base, and what is called activity coefficient. Basically, suppose we have the A plus B and it is going C. So concentration of A or activity of A, that is concentration of A plus into gamma plus. So this gamma, that is the activity coefficient, and A plus, that is third bracket it is showing, that is the concentration. Okay, so these things we have discussed, and so many things. And acid base equilibrium in water also we have discussed, and ionic product. So basically when water is there, that will dissociate to H plus and OH minus. So ionic product Kw, that is concentration of H plus into concentration of OH minus. So and it is usually 10 to the minus 14 value. So that means H plus concentration, it will be 10 to the minus 7. So these things we already discussed in the class. So pH, basically pH represent the minus log of H plus concentration. Okay, after that we have discussed the common ion effect. So common ion effect, basically what it is to tell, that this as example, that acetic acid, which is a sparingly soluble salt, means soluble weak acid, basically it will sparingly dissociate. So it will some amount, it will be H plus C, CH3C double O minus, and H plus it will form. Now if you add any CH3 sodium acetate, then what will happen, that in the system CH3C double O minus, it will concentration will increase. So what we will do, that it will try to go to the left shift, means some of the CH3 O minus that will react or coordinate with H plus and it will form CH3OH. So the equilibrium it will shift to the left side. So this due to this sodium acetate or acetate lithium acetate ion it is shifting. So in both cases this ion is common. For this it is called common ion effect. Okay, then we discuss about the buffer solution. What is buffer solution? Basically, buffer solution is the solution which resists the pH of the solution when you add small amount of acid or base if you add in the solution. So that is the buffer solution. From there we can calculate the pH. What is the pH of buffer solution? That's depend on the pK value of the acid and Kb value of the base. So these things, along with that, we have discussed about lots of things, lots of information or problems on solubility product. So basically, suppose you have AB, it is going A plus and B plus. So solubility product KSP, that is concentration of A plus into concentration of B minus. So this product that we can calculate the solubility product of salt. So silver chloride, like then the KSP value that will be concentration of Ag plus concentration of Cl minus. So that kind of thing. Along with that, we have discussed, I think this is the picture of electrochemical cell generator where you have the sample gas diffusion barrier. So you have the electrode, counter electrode you have, and you have the porous working electrode where your gas will absorb and reaction can be happen. So this is we have discussed in different later class also. Okay, now in the week 3, what we have discussed? We have discussed the electrochemical methods, basically electrogravimetry, where basically you have the electrochemical cell, what I have shown in the video. So, and you have taken the electrolyte, and along with that, you have the two deep electrode you have put, and this lead it is connected with the potentiostat, whatever I have shown there in the video. So, there it is 3 electrode, but when you will do the electrogravimetry, then what is called you can use the true electrode. In that case, what you have to do, electrochemical working electrode will be same, but counter electrode and reference electrode to lead you have to add. After that, you have to connect with one lead. So that this is your one electrode and this is another electrode. So this is electrode 1, this is electrode 2. Okay, so after that you can apply the potential in the electrochemical cell. And here also we have discussed the Faraday's law, that one Faraday if you apply in an analyte, then one equivalent equimolar of that compound will be deposited. So these things, Faraday's law, as I have mentioned, then cell, some of the term whatever I have shown, cell, electrochemical cell, voltaic galvanic cell. So okay, then how the relationship of the lambda conductivity with the volume of the solution, and this is the lambda conductivity as a function of the concentration, where you can see this is for strong electrolyte and this is for weak electrolyte. So here you can see for the strong electrolyte, when you are dilute the solution, it is conductivity is highly increasing because it is fully dissociate, and when you dilute the solution, the ion of the dissociate ion that will going far away to each other, so there is no interaction to each other, so that ion is act as a gaseous particle kind of thing, so that the movement will be high, so the conductivity will increasing. So for the, it is linearly increasing, but in the aqueous weak electrolyte, why it is increasing, that we have discussed, that weak electrolyte it is not fully dissociate. So when you are adding the water, then it will dissociating, so the number of ion is increasing in the solution. So as the number of ion is increasing, the conductivity value is increasing. For this, it is rapidly or suddenly rising the conductivity. So all these things we have discussed, and from this table what we have discussed, that why H plus ion has a higher higher conductivity value, and when we are going lithium to sodium to potassium, the conductivity value for lithium is low, and when it is going sodium it is increasing, and potassium it is increasing. Why it is increasing? Due to the solvation sphere. So that we already have discussed. Okay, now okay, and how to calculate the cell constant. So this is the electrochemical cell. So we have two parallel electrode. Now you want to know what is the cell constant. Basically, you have to calculate the L value and A value, area of the value. So you can know the area, or you can measure the area of the electrode, but the distance between the two electrode is not possible. So for this, what we used to do, that we have taken a standard solution like different concentration of KCl, and the conductivity value of this KCl solution we know, and you can plot R versus rho value, and you can get the from there the cell constant. Okay, so that things we have discussed in details. Okay, and this is different type of electrochemical cell picture. And galvanic cell, we have discussed galvanic cell where the chemical energy is transforming to electrical energy, and electrolytic cell where electrical energy is transforming to chemical energy. And equivalent conductance or specific conductance, that what is called equivalent conductance, basically the specific conductance into volume of the solution in cc, which is contain 1 gram of equivalent of electrolyte. So that things we have discussed. After that, we have discussed the Colora's law. Colora's law, what it is to tell that at infinite dilution, the total conductivity of any electrolyte, that is the summation of the cation conductivity as well as the anion conductivity. So that is the Colora's law. And conductometric titration. So what it is to tell, that you have the electroanalytical cell, and you have two parallel electrode, and this is the mixing thing, and you can drop wise you can add the solution, and you can measure the potential or current value, and from there you can measure the conductivity value. Okay, so I think here I can show, I'll show the potentiometric titration how to do. That video I'll show. And this strong acid versus base titration, how it is to do. So it is decreasing initially linearly, it is decreasing. After that sometime it is increasing, because initially you have H plus which conductivity is high, so this H plus is replacing by the Na plus, so which conductivity is low. So for this it is linearly decreasing. After some time when the end point is come, after that you are adding excess amount of NaOH, so that in the solution your OH minus concentration is increasing, at Na plus ion concentration is increasing. For this the conductivity value is increasing. Okay, so that things we have discussed. And for strong acid versus weak base also we have discussed how, why it is happening, and different concentration of conductivity. So these things we have discussed. I think we can go to the next is potentiometry or galvanic cell. So this is whatever I have shown in the video, that earlier what is to do, that we have electrolyte in two beaker which is separated by the salt bridge. But whatever I have shown in the electrochemical cell, all the electrolyte is there, and your this is, suppose this is reference electrode which is connected with the feed, means what is called salt bridge. But in the whatever the video I have shown, that your reference electrode is separated by the feed which is acting as a salt bridge. Okay, so in this way, and your potentiometer is there, and that is connected with the electrochemical cell. So that things, and then after that we have discussed the double layer and double layer electrical double layer, where you have the electrode, and in the electrode surface, if it is positive, then negative charge will absorb on the surface, and after that the intensity or concentration of negative charge will be high. And this part, this is called inner Helmholtz sphere, and this is outer Helmholtz sphere. So this distance 20 to 300 Armstrong, and where you can see that as the distance of the or distance of the double layer is increasing, or thickness of the double layer is increasing, the potential value, potential difference is decreasing. Okay, so that things we have discussed. Then after week 4 we have discussed potentiometry. So basically whatever almost same, and from there we have discussed the Nernst equation, all these things. After that we have discussed the polarography, how high this current value is steady state, that also we have discussed, as new drop of the mercury is forming. So for this there is no such a diffusion, so there is a steady state is coming, because your fresh electrode surface, the fresh Fe3 plus is or Fe2 plus is coming and contact with the working electrode surface. Okay, so and after that we have discussed Karl-Fischer titration, and on Karl-Fischer titration also we have discussed lots of problem. And then week 6 whatever we have discussed the, yeah, so this week 6 whatever we have discussed different type of cyclic voltammetry part. So basically heterogeneous, homogeneous electron transfer rate constant, all these things. And whatever we see that in software this kind of dark shape of graph is observed. So this is the oxidation, this is reduction. Now you get to know that whatever we have discussed in the class, practically how it is to do. Okay, and this is the electrochemical cell whatever we have saw in the video. Then solvent, why, what are the properties is require solvent. So and supporting electrolyte, what are the things. So as I have seen that it is chemically and electrochemically inert. So for that, when we have done the cyclic voltammetry of the analyte, before that we have taken the cyclic voltammetry of the supporting electrolyte. So we have seen that it is coming straight line. That means it is enough in that electrochemical potential window, right? Now, okay, all these things. And yeah, so there we have given 4 segment, no. So basically from D to G, this part, this is one segment, and this is another segment. So for one cycle there is 2 segment, so I have given 4 segment, that means 2 cycle I have run the cell. Okay, so these things we have discussed. Okay, now Rayleigh-Sevig equation. So here you can see IP peak current, basically 0.446 NFA C naught NFA D naught RT. Okay, here this new, that is the scan rate. Okay, now if you do the experiment in different scan rate, and if you plot IP peak current versus mu to the scan rate, then you will get the current value for different scan rate. It will be a straight line. Now if you basically you are plotting IP versus mu to the scan rate. So from slope, what information you can get, number of electron n value you can get, then d to the half diffusion coefficient you can get. Okay, so and you know the area and concentration of the bulk electrolyte, all these things you know. So that means it is quite interesting and fundamental experiment, where you can get that how many electron is participating in the Faraday reaction. Suppose it is going Fe3 plus to Fe2 plus. So suppose you have taken some what is called electrolyte, and suppose Fe3 plus electrolyte you have taken, and you want to do that some redox couple you have observed. Now you want to know that it is going to Fe3 plus to Fe2 plus, or it is going to Fe3 plus to Fe naught. So in that case you can calculate the number of electrons from the cyclic voltammetry, and then you can get that okay, this is if it is n is equal to 1, then you can tell that it is going Fe3 plus to Fe2 plus. If n is equal to 2, then you can tell that it is going Fe3 plus to Fe naught. Okay, so that things you can get the information. Then we have discussed that electroplating. So basically you have the 2 electrode and electrosensing application. and then Grant's plot, how to calculate the concentration of the analyte, all these things. Then week 7 we have discussed the biochemical fuel cell. So all this information we have discussed. Then different type of biochemical fuel cell like indirect cell, direct cell, all these things we have discussed. Recently we have discussed these things. For this I am not going to details. Okay, and then we have discussed different cyanide OS treatment. So there is 10 different type of process is there. So I think I would suggest you people that you can remember all these things, because I think in the exam they can ask this from this part, they can ask the question. Okay, cyanide waste, because it is quite a important waste handling treatment. Then week 8 we have discussed the what is called battery technology. So basically we have discussed why we need to do the why you need the electrochemistry, because it is quite interesting that you can control the CO2 emission, energy consumption day by day it is increasing. So that electrochemistry that can save our world. So and in among the battery technology, one of the promising candidate where you can store the renewable energy, and you can use the renewable energy source, because solar, wind, all these things which is controlled by the nature, so that energy you can store in the battery, and you can use at your necessity. But for that we need the high energy or high capacity battery. So here we have shown that lead, earlier people used to use lead acid battery, but you can see here the lithium ion battery which has the gravimetric energy, high gravimetric energy, as well as volumetric energy density is quite high. Okay, so this is things. Now we have shown these two equation, how to calculate the power density as well as the energy density. That is basically the multiplication of the potential and the current value with time, and divided by the mass of the battery. So and the power basically that will give the information that with time how the energy is changing. So and from here we have discussed that different type of battery. Okay, so lithium ion battery which has the higher energy density. So for these people are interested on lithium ion battery. So for lithium ion battery, these three men great man has elected as a Nobel laureate. No, they got the Nobel Prize in 2019 due to development of lithium-ion battery. So John Goodenough from USA, and M. Stanley Whittingham from UK, and Akira Oshino from Japan. So these three person got Nobel Prize in 2019. Okay. Okay, and I have shown that how the electric vehicle in India market is more interested in electric vehicles. So this is one of the time scale diagram where you can see with 2030 most of the electric vehicle are depend on the battery energy storage. So here you can see this sky blue color that is representing the plug-in hybrid electric vehicle. Basically, hybrid electric vehicle means we have the battery as well as petrol also. So car can go run by battery as well as petrol. So here you can see with time the battery demand is increasing. So the fully battery vehicle is running. So and some of the top electric vehicle company in India, they are more interested, and they have developed they have opened a research and development section for the electric vehicle. So basically they are developing the battery to use in the electric vehicle. So after that we have discussed the ion battery, lithium ion battery. So lithium ion battery basically we have the lithium manganese metal oxide in cathode side, and the anode side we have the graphite which is a lithiated, that is acting as a anode, and during the discharge and charge lithium can go or intercalate and deintercalate. So here this graph it is representing that lithium ion battery which has the energy density around 360 160 watt per kg. So but for next generation electric vehicle we need the energy storage of battery which has very high energy density. So here in this graph we can see the lithium air battery which has a very high 10 times higher energy density, and it can compete the gasoline. So and this diagram representing different metal air battery, where you can see for lithium air battery it is high energy density because lithium it is very light element. So for this it is high energy density. So after that we have discussed the metal sulfur battery. So in the lithium ion battery, basically lithium is intercalating and de-intercalating. But in the case of metal sulfur battery, basically sulfur, which is light element, that is converting in different sulfur and polysulfur component like S62 minus S42 minus. This is during the discharge process, and during the charge process, reverse process is happening where Li2S form it is converting S22 minus, then S42 minus, and ultimately it is converting to the sulfur. And if you do the cyclic voltammetry, whatever I have shown, you will see this kind of graph of current versus voltage. Okay. So after that we have discussed zinc air battery. So and zinc air battery, whatever we have a zinc metal as a anode, and in the porous cathode side is there, so oxygen can come and it will reduce as the air cathode, and OH minus it will form. And the in the zinc anode, OH minus react with the OH minus, it will form zinc hydroxide, and ultimately it will transform to the zinc oxide. Okay, so this is one of the and this is non-aqueous calcium and magnesium air battery, as well as lithium plus and sodium plus, that kind of also battery is there. So basically you have the metal anode, same thing, and in the porous cathode side is there, which is separated by the electrolyte. So your air can come and dissolve in the electrolyte, and it can reduce in the air cathode. So but this reduction or oxidation of the air is very difficult. Sluggish kinetics. For these people use the catalyst. So there is two type of catalyst. One is electrode catalyst and electrolyte catalyst. So electrode catalyst we are using in the air cathode, and electrolyte catalyst we are using in the electrolyte. Okay. So that also known as the redox mediator. So these things. So yeah, electrolyte cathode that we used to call as a redox mediator. And we have shown this part that hemoglobin is one of the case study our group has done, and I also have done in metal phthalocyanine as a redox mediator. So up to this we have discussed. Okay, so now I think we can, so I can show whatever we have discussed in the class, that things I have shown. So basically summarize all the part. Okay, now I can show what are the I hope all people just get whatever you have discussed. I can show now the conduct of potentiometric titration part. Okay, what happened? Okay, so that potentiometric titration, okay, that thing I can show. I think let me share the that part. Okay, so this is the video, basically potentiometric determination of mixture of halides. I think these things we already have discussed. So this video we have done in Bangalore. So I was the TA of UG course. So that time during the COVID, I think. So that time we have make this video. So during that video course, Professor Vivek Tiwari was the course instructor, and the lab instructor was Chinta Jana. So he helped a lot to make this video, and I was the TA of this course. So basically, I think okay. Okay, so these are the chemicals which is required to do this experiment. So basically, the aim of this experiment is that you have they have given one different mixture of halide. So potentiometrically, we want to know the concentration of different halide. Okay, so that was the motivation of this experiment. So you can do the colorimetric titration where you are basically try to check means due to the color change you can get the endpoint, but in to detect that thing means color change, sometimes it's difficult to detect the endpoint by color change. So for this potentiometric or conductometric titration, it is quite easy to get the endpoint exactly. Okay, so for that what is called, you need all these things. So distilled water, silver nitrate, sodium chloride, potassium ferricyanide, and PESCO. This is PESCO ORP probe. This is basically the electrode. Whatever we have discussed in the class, that glassy carbon electrode. Sorry, not glassy carbon, glass electrode we have discussed. No? So this is PESCO ORB probe. That is that kind of electrode. Okay, so we'll see that part only. And Bourret volumetric plus all these things. So this is the all other things I think we people know. So this is a step involved. So first things is you have to standardize the silver nitrate because you have the halide solution. So that means if you titrate with silver nitrate, then what will happen that in the solution silver chloride precipitate will form. So that in your solution the ion number of ion will be decreased, so that current response will be changed, and from that your potential also will change. Okay, so from there you can get the endpoint of the titration. Okay, so this is the step. First you have to standardize the silver nitrate solution, then potentiometric titration of unknown concentration of halide solution, then you have to calculate the things. So I think first step is you have to make the solution. I think that things. So I think all these things you know that first you have to weight the silver nitrate, because silver nitrate, which is a what is called secondary standard. So secondary standard means what is called the whatever concentration you will make, that will not exactly same. Suppose you have made is 0.1 molar of silver nitrate solution, but if you measure the concentration of silver nitrate solution, that won't be exactly 0.1 molar. So for this, what people is to do, that secondary standard, that will change with time as well as with what is called with temperature, all these things. So for these people is to do that, to know the exact concentration of secondary standard, that is to standardize by the primary standard. So here here what is basically it is same. Earlier also we have shown this thing that how to make the solution, all these things to make up the solution up to the mark, and you have to shake rigorously. After sorry, after that transfer the 0.1 molar silver NaCl solution. So this is the primary standard of NaCl solution. So that will be standardized by silver nitrate solution. So we have taken 10 ml of NaCl solution, and we are using the potassium chromate solution as a indicator. So 1-2 drop of potassium chromate we have add. Now we can titrate. So I think you all people know how to do the titration, all these things. I think you have done in the UG or during MSc in physical chemistry lab. So it will be white, milky white kind of solution. It will be. At the end point, it will be milky white. So now you can get the reading from the from the burette. So what is the concentration? Then from here you can what is called, you can measure the things. I can skip this part because you have to do the this experiment 3 times, as you all people know this thing. So I will go to the probe part, this conductometry titration part. So this is basically I am repeating 3 times. Okay, so this is basically the analyte or standard solution. Rinse with pipette, with water, all these things. I think these things you people know. Okay, this mixture we have taken 10 ml of solution. So in 10 ml of solution, and we are taking in the beaker because we have to put the what is called probe, not probe. So basically, electrode we have to take. So that PRB electrode. So that conductor volumetric, voltammetric titration we have to do. So that why we are taking this thing. And as this 10 ml solution, we are adding 50 ml of water so that the volume of the solution will be high, so that you can dip the electrode in this solution. Okay, so I think one picture we have shown that we have the electrode and some steering solution electrode is there, and that is connected with the potentiostat. So to measure the potential of the solution, so that kind of thing. So you can see, so on the top we have put the burette, from where you can put the silver nitrate solution, and in the beaker we have taken the mixture of different silver the halide, mixture of halide, and you can fix all this part. Okay, so this is the Pasco ORP Pro wireless. So this is wireless, means in a laptop we can install the software and it can be connected by the Bluetooth. Okay, so no need any connection or no need any wire connection of that probe. So it is quite interesting. And this probe is quite cheap. It is means around what is called 16,000 or 15,000. So this is the electrode. Whatever glass electrode we have discussed in the class, no? So this is that kind of thing. Okay, so in the top below part you can see there is a tube kind of thing, what is called spherical kind of uh, glass electrode is there. So which is a glass electrode is ion specific transport membrane is there. So I think all these things we have discussed in the class. So for this I am showing this video so that you people can get in-hand experience. Mm. Not in hand, basically means you can see the electrode how it looks like. Okay, so this is the thing. So in this part you can see, okay, here in this part you have the what is called this glass electrode is there. I think in this part. Okay, in this part you have the glass electrode. So and whatever things we have to clean properly the working electrode, because uh, if you have water or all these things, then the pH of the solution can change as well as the concentration of the solution is changed. So here you can see spherical kind of some glass electrode is there. Okay, then there is a adapter, so which can connect your electrode with the what is called software. So with your PC. So this is the adapter. Okay, and there is a one power button is there. So to switch on the device. Okay, so this is the Bluetooth Pro Pasco wireless pH meter. So it can measure the pH also. So you can do pH dependent conductometric pH dependent measurement also, as well as you can measure the volumetric. Okay, so this is the interface so of the PC. So you have to go and for this. Okay, so open Spark View software. So this is the software for this electrode. So if you open this Spark View software, then it will this kind of interface it will come. Now it will show to connect the Bluetooth. So here you can connect the Bluetooth like this. So green light will blink. Now you can see the green light is blinking. That means it is connected with the device. Okay, so now what you want to in this case here you can choose that you want to measure the pH or you want to measure the voltage. So with one electrode you can do all these things. So you can measure the pH as well as you can measure the voltage also. Okay, now as we want to do the titration, so that means you are adding the volume of the what is called analyte. So as is silver nitrate, here we are using silver nitrate. So from the burette you are adding the silver nitrate. Then you can dip the electrode in the beaker. And to steer the solution, you can switch on the magnetic stirrer so that it will mix the analyte properly. From the burette, you can what is called, you can put the analyte. Okay. So here you can see there is a change in the what is called potential. It is giving the potential. Now, how much analyte you are adding, so that you can put in the x-axis, and in the y-axis it will give the potential. So when you are putting the your drop wise, you are adding silver nitrate. So from the burette data, you can get how much silver nitrate you have added. So that things you can write in the X column. As I have discussed, that it will give a sharp change when there will be an end point. So here you can see, so it is rising where first your silver nitrate, it is silver nitrate, it is reacting with the halide salt, and silver chloride or silver bromide, that is forming, and it is precipitating. So that will change the potential of the solution. For that, there is a high sharp change of the potential, and from there you can get the equivalent point. Okay. So in the solution, you can see as the silver halide salt is precipitating, that that's why it's become little bit sluggish. So earlier it is a clear solution, it was. So now it's become little bit sluggish. So 3 halide mixture is there. So basically 3 hump you will get. Okay, this is first hump we have got. So basically, whichever solubility product is low, that will precipitate fast. Okay, so from here you can get that which one it will first precipitate. Suppose you have the mixture of chlorine, bromine, and iodine. Then, if the iodine solubility product is low, then it can precipitate fast. So the first hump, it is due to the silver iodide precipitation, so that kind of thing. So if from here, what you can get, that you can get the information Okay, in the chat box, someone has written, Barun has written, sir, please share your WhatsApp number. If I get any doubt about the problems, I will contact. Okay, Barun, I cannot give the WhatsApp number, but I can give the my mail ID. Okay, so that you can send the things in mail. Okay, because I usually active in the mail, so you can send the mail to me. Okay. So in Anil has asked, sir, in exam universal constant is given or not? Okay. Universal constant means R you are asking? So R value usually people did not give in the thing because all people know the R value. So that you can remember. Mm. So here you can see that 3 harms we are getting. So here you can get the concentration, uh, how much concentration of the halide. So from the V1 S1, V2 S2. So that formula you can use and you can calculate the concentration. Okay. Barun, I'll write the what is called the mail ID. I think I already given in the chat box also earlier. Again, I can give my mail ID. Okay, so this is my mail ID. So anytime you can what is called you can send me the mail. So I'll okay, as soon as possible I can reply to you people. Okay. So this is the things. If you people have any also, or you can send me the via mail also. So as soon as possible, I can reply to all. Okay. So this is all up to this, and yeah, as I have mentioned, electrochemistry technique is quite interesting. So you people can uh, do so many things in electrochemistry. So if you people are interested in electrochemistry, people can contact any professor in IITs, ISC, or IJAR. So there you can do your PhD as well as you can do your intern master project also. So all these things you can do. Okay. So that's all, and all the best, all the people to for your future. And we'll okay, if in future we'll get any chance, then we can meet again. Thank you all. I think I can conclude this class here. So if you people have any doubt or any question, please write to me in mail. I'll okay, reply in mail. Okay. So thank you all for joining, and we'll meet again.